Hey students, how are you guys? So this week I'm going to be doing some work on, or giving you an overview for minerals, since this is your topic for this week. So as always, these videos are just optional. They're things that I put out there to help you a little bit, and hopefully they will assist you in your study. Okay, sorry about that. So just to remind you, in your announcements that I send out, and also in your overview, there's actually a set of objectives for each of your chapters. And this is what I'm going to be kind of hitting on really quickly. This is what you should be focusing on in your text and to look at. Now, this is just my notes page that I get ready for the week, but it's also in your introduction, in your overview for this week as well. Okay, so anyways, let me get back to the material, and I'm going to try to just kind of walk through this really quickly. So as you might already know, I used to teach this actually at BYUI on campus for a while, but since I've left and am now working at Utah Valley University. These are some of my slides that I used when I was at BYU Idaho, and so and I've adapted them a little bit just for how you guys actually are teaching. And so just wanted to kind of go through here. First of all, let's start off with what is a mineral. A mineral is a naturally occurring inorganic and homogeneous solid. I actually like this format. This is one of my slides from UVU. This is actually one of my favorite ways of looking at this. This is a flow chart. Minerals are combined, are basically, let's say, let me go through this here. Here we go. Okay, are crystalline, chemically homogeneous. That means that each mineral has the same thing, like silicon and oxygen, or just copper, or just gold, or something like that. Okay, they're made of elements. They have to be crystalline, chemically homogeneous, solid, coherent. Okay, means they're sticking together, right? Okay, and natural. Okay, that's what makes a mineral. Now, rocks are accumulations of minerals that can be either igneous, sedimentary, or metamorphic. Okay, that are then used in products that we call mineral resources, and then that can be mined. If they're mined economically, they're what we call mineral reserves. Okay, and so but it's important to understand that these subtopics here at the start, and they're naturally occurring, inorganic, homogeneous, has a definite chemical composition and a definite chemical structure. Okay, whereas a rock is just a bunch of minerals put together. Okay, so note the difference between these. So, for example, here's some examples of minerals. Hematite, that's made for the ore of iron and steel, bridges and stuff like that. Quartz, which is used in glass, computers. Pyrite, used to manufacture sulfur, which is often called fool's gold. Gypsum, which is drywall, plaster, fertilizer. Gypsum has a lot of water in it, and because of that, it's actually a fire retardant. This is part of the reason they use it in drywall, plaster. Okay. Galena, which is used of iron, batteries, radiation shields, fishing weights, like that. Anything that has lead in it, because that's one of the chemical composition of galena is a lead sulfate. Okay, calcite here is used in cements, toothpaste, mortars. It's actually in your Cheerios as well. They crush it up and put it into your Cheerios for calcium. Okay. Fertilizer, film, so they're used for a lot of different things, okay? And so they have lots of different ideas and things from it. So remember, the minerals make up the rock, but the mineral has these individual things, okay? So here's some examples of some objects. Which one of them are minerals? Well, bones aren't, because they're organic, right? They're derived from organic. Sometimes our teeth, they say, well, they're mineralized. Well, that's just what we call a pseudomorph, or a pseudo mineral, which means that they're kind of mineral-like, but they don't have all the characteristics of a mineral. Okay, so that's an example for like a bone or a shell. They're mineralized, but they're not a pure mineral because they don't have all those characteristics that we talked about before. Water can't be a mineral because obviously it's not a solid. Coal is made from organic material, so it's not a mineral. So in this case, it's ice. Ice is, if you look at it, if you think about it again, ice is, let me go to that. It's crystalline, it's chemically homogeneous, it's H2O, right? It's solid, coherent, and natural. So ice would absolutely be considered a mineral. Okay, but if it's in a water form, it's not a mineral. If it's in a gas form, it's not a mineral, right? Okay, here's another set. Synthetic diamond, obsidian, emerald, amber, petrified wood, amethyst. All of these here are either mineraloids or minerals. But the ones that are minerals here are an amethyst is a mineral. Okay, so is an emerald a mineral. Okay, both of these are minerals, but none of these other ones are. A synthetic diamond is one that actually is made by humans, okay? So it's actually compressed carbon in a sense to form synthetic diamonds. Obsidian is actually a type of rock. It actually has lots of different minerals inside of it. It's volcanic glass. Okay, and glass is that as well. It's not a distinct structure, so therefore it is not a mineral. Amber is organic in nature. It's usually tree sap. Same thing for petrified wood. If you actually look at the quartz inside of it or the calcite inside of petrified wood, that could maybe be a mineral, but the wood itself, no. Okay, so these are just examples of some of those and how we use it. We use it for lots of different things. We mine that stuff from all these different minerals to actually use in our different materials, like our smartphones. We get iron and aluminum and copper and all these things for different parts of our smartphone, right? So we have to mine it from all these different places just to get it to our smartphone. Okay, so how does these minerals or these different elements combine? Well, they combined by through different types of bonding, right? And so they are bonding because of the different atoms that are within them. Okay, so and their structure. So what protons are there, electrons, neutrons, and so forth, and how they actually react with one another. So, for example, in ionic bonds, what happens is there's one leftover, one more electron is needed in this outer shell of chlorine, and then whereas sodium has one leftover electron in its outer shell, so by actually combining they're attracted to one another because the chlorine wants that extra electron, and sodium wants that outer shell to be filled. And so what it basically does is it basically gives its electron, in a sense, to chlorine, and it actually, that electron now no longer goes around sodium, it actually only goes around chlorine until it actually separates again, and then sodium has to have that electron back. Okay, but once it's actually bonded together, we bond it through what we call an ionic bond. That electron actually no longer goes around sodium, it actually goes around chloride. And I actually, the way I help people remember this is that sodium gives up its electron and for chlorine, and so chlorine keeps it. It's very independent on itself, for itself, or so forth. Well, if you only do things by yourself, it's not as strong as if you do something together. And so these are fairly strong bonds, but they only have moderate hardnesses because you can break them apart quite easily. For example, sodium and chloride, it's easy to break apart. That's basically salt, right? And so and the way to do that would be just to add water. And the water, because it is a polar bond, actually will separate these two and then actually go apart. Now, sodium by itself is actually a very reactive metal. Chloride by itself is a very reactive gas. Put them together and it's inert. It doesn't actually have much of a reaction at all, right? And so that's what we call an ionic bond. A covalent bond are very strong bonds. They're ones that are basically, in a sense, working together. They're actually, and I think about this back to being a selfish ionic bond where chlorine just keeps the electron by itself, doesn't share it with sodium, but whereas in covalent bond, they're actually sharing those electrons. So for example, here is, I think this is fluoride, and fluoride has this 1, 2, 3, 4, 5, 6, 7 electrons in its outer shell, and same over here. And so what they're saying, well, I want my full outer shell full with 8 electrons would make it full. And so what they do is well, let's do this. Let's share an electron. So what this fluoride atom does is its electron goes around fluoride, but then it also goes around this one. It goes around this one and goes around this one. That's the same thing for this fluoride one, is that it goes around, theirs goes around one, and there's one of theirs goes around there. And so what happens is because they both want that electron, they actually come very close together, and they're very strong bonds. Okay, and so they're covalent bonds. So like like a marriage, where they're coming together and working together, and it makes it a strong, strong bond. So covalent bonds are some of the strongest bonds out there because of how that happens. There are other types of bonds as well, like metallic bonds or van der Waals bonds. These are fairly weak bonds. Van der Waals bonds are very, very weak, and it's just this weak attraction. It's kind of like where water is attracted to the edge, the outside of your glass, right? It's this polar bond in a sense where one side's negative, one side's positive, so you have this kind of weak bond between the two, and that's what we call a van der Waals bond. A metallic bond is a little bit different, where the electrons are shared all the way throughout there. Because the electrons are shared, the atoms themselves are not in a rigid structure, so they can bend and push and pull and stuff like that. This is what makes metals able to bend, right? And also what makes metals electrical, have high electrical conductivities, because the electrons just kind of go through and are shared as it goes through the wire. So electron goes on one side, electron goes on the outside, because that's all electricity is our free electrons. And so, so those are different types of bonds. And these bonds are what make the actual atom or the mineral actually come together, okay, to actually form its chemical structure. So here's an example of a chemical structure. This is what we call a silicon tetrahedron, where there's 4 oxygen bonding covalently to that silicon, which is strong bonds, right? And this is actually a very common structure in the Earth. And the reason is because there's lots of oxygen in the crust and lots of silicon. It's the 2 highest minerals, and so we have lots of these type of minerals. They're called silicate minerals because they're made up of silicon and oxygen. So the most common silicate mineral is quartz, which is SiO2, okay, which is basically silicon with 2 oxygen, okay. And so what basically is happening here is they don't have their full charges met, so they actually try to covalently bond with each other in these chains. And so you have what we call a double chain, a single chain, double chains, or sheet structures, which are sheet chains in a sense, okay? And they bond together because of those chains. And so they'll form different structures where, like the quartz here has it, so it has what we call a framework structure, where they're actually, these sheets are basically are on top of each other, and all of them are covalently bonded. And so they're really hard in all directions, and so that's why quartz has it's very hard, okay? It has a very rough structure or rigid structure to it. Whereas biotite, it has a sheet structure as well, but that sheet, the top sheet and the bottom sheet are not connected in a sense. There's other bonds like van der Waals bonds or that are actually in between them, like these ones here, and therefore they break off in these sheets, okay, these little sheet type minerals. So both quartz and feldspar are what we call framework silicate minerals, and then some of the other ones have what we call double chains and stuff like that associated with them there. Some feldspars are double chains, but most of them are framework. Okay, so here is an example of halite, where it will actually be, because of the way it bonds, they always want to bond in a cubic fashion. Okay, and so if you look at your salt, it will always be in a cube. Okay, whereas some other minerals will form more in a kind of this diamond shape, like a diamond. That's why, part of the reason why it's actually called that, right? Okay, and so, but these minerals all have these very strong covalent bonds, and so they're really hard. That's why diamonds are one of the hardest minerals in the world, whereas graphite has these weak bonds to them. Even though they're both carbon, it's the exact same element, they're bonded in a different way to make graphite very soft and diamond very hard. Okay, this has all these covalent strong bonds. These have all these weak bonds. Okay, so minerals are actually known by their physical properties, the way that their crystals form, the way they break, which is either cleavage or fracture. I need to stop here in a second. Okay, the luster is the way that it shines. The color, be careful about that one. That's kind of tricky. The streak is how it actually grinds into powder. Its hardness, specific gravity is its density. Okay, so all of these will help us to understand which minerals they are. So minerals can form because of igneous features, where the magma, where actually the elements will start to cool off, or it can be from other ways like concentrations and stuff like that.